In the constellation Bootes, there exists a hole in space, so massive that it could swallow 1,000 Milky Way galaxies and still have room left over. This is not empty space between stars or even between galaxies. This is a region where galaxies themselves simply do not exist. Scientists call it the Bootes Void, and its discovery shattered our understanding of how the universe should look. We will journey into this cosmic abyss, explore the few lonely galaxies trapped within its boundaries, and discover how this great nothing forces us to question everything we thought we knew about reality itself. If this journey into the universe's darkest secret intrigues you, hit that like button and subscribe for more cosmic mysteries. Prepare yourselves. We enter the void. In 1977, astronomer Robert Kirshner pointed his telescope toward the constellation Bootes and found absolutely nothing. Not the faint glow of distant galaxies, not scattered star clusters, not even cosmic dust, just emptiness stretching so far that light itself seemed to disappear into the black. Kirshner had stumbled upon something that should not exist according to every model of how the universe works. You have to understand what makes this discovery so disturbing. When we look into deep space, we expect to see galaxies everywhere. They should be scattered across the cosmos like cities viewed from an airplane at night. The universe, we believed, was relatively uniform. Matter should be spread out fairly evenly, with galaxies forming a cosmic web of light stretching in every direction. But this region of space broke all the rules. Picture this. If you could shrink the Milky Way down to the size of a quarter and toss it into this void, you would need to throw 999 more quarters to even begin filling the empty space. The void spans 330 million light-years across. That means light, traveling at 670 million miles per hour, takes 330 million years just to cross from one side to the other. Think of it like finding a perfectly empty parking lot in the middle of Manhattan. Except this parking lot is bigger than Manhattan, bigger than New York State, bigger than the entire continental United States. It is a region of space where matter simply chose not to exist. The discovery sent shockwaves through the astronomy community. How could such a massive region contain almost nothing? Where did all the matter go? Did it never form there in the first place? Or was it somehow pushed out by forces we do not understand? Kirshner named his discovery the Bootes Void after the constellation where he found it. Other scientists began calling it the Great Nothing or the Cold Spot. As more powerful telescopes turned toward this region, the mystery only deepened. Survey after survey confirmed the impossible. This was not just a gap between galaxies. This was a hole in the very fabric of the universe itself. The void challenged everything astronomers thought they knew about cosmic structure. If the universe formed from tiny fluctuations in density after the Big Bang, how could such a massive region remain so completely empty? What force could be powerful enough to keep galaxies from forming across such an enormous volume of space? As Kirshner continued mapping the void's boundaries, he realized he had found something far stranger than anyone could have imagined. The emptiness was not random. It had structure. It had purpose. And deep within its heart, a handful of galaxies hung in the darkness like lonely islands in an infinite ocean. But these survivor galaxies held secrets that would make the mystery even more terrifying. When astronomers first calculated how many galaxies should exist in the Bootes Void, they expected to find around 2,000 bright star-filled systems scattered throughout the region. They found 8. 8 lonely galaxies floating in a space that should house 2,000. Imagine walking into a concert hall designed for 2,000 people and finding only 8 scattered individuals sitting in the darkness. The silence would be deafening. The emptiness would feel wrong at the most fundamental level. These 8 survivor galaxies became known as the Void Galaxies, and they defied every rule about how galaxies should behave. Normal galaxies live in neighborhoods. They cluster together, gravitationally bound in groups and superclusters. They trade matter back and forth, sometimes colliding and merging over billions of years. They exist in a cosmic society where no galaxy truly stands alone. But the void galaxies are different. They are cosmic hermits, isolated beyond anything we have ever observed. The nearest neighbor to any void galaxy is typically 50 million light-years away. For comparison, our closest major galactic neighbor, Andromeda, sits only 2.5 million light-years from the Milky Way. The void galaxies are 20 times more isolated than we are. This isolation has had profound effects on their development. Without nearby galaxies to interact with, they have evolved in cosmic solitude. Many are surprisingly small and dim, as if the emptiness around them has somehow stunted their growth. They contain fewer heavy elements than galaxies of similar age in normal regions of space. Their star formation rates are unusually low, creating galaxies that seem almost sleepy compared to the bustling star factories we see elsewhere. Scientists call this phenomenon galactic underdensity. But that sterile term cannot capture the true strangeness of what we are observing. These galaxies are not just separated by distance. They are separated by an emptiness so profound that it affects their very nature. They are like children raised in isolation, developing differently than they would in a normal cosmic environment. The mathematical probability of finding such massive underdensity by random chance is less than 1 in a million. The universe should not be able to create such emptiness through normal processes. The Big Bang should have left behind tiny variations in density, but those variations should average out over such large scales. Finding a region this empty is like flipping a coin and getting heads 1,000,000 times in a row. Yet here it exists, challenging our most basic assumptions about cosmic evolution. The void galaxies themselves seem to know something is wrong. Their peculiar properties suggest they are shaped by forces we do not yet understand. Forces that can carve massive holes in the fabric of space itself. The mystery deepens when we examine exactly how these 8 survivors are arranged within their cosmic prison. The 8 galaxies trapped within the Boots void are not scattered randomly throughout the emptiness. They are arranged in a perfect tube. Picture a massive, invisible subway tunnel stretching across 300 million light-years of space. Now imagine 8 subway stations evenly spaced along that tunnel, each one glowing with the light of billions of stars. This is how the void galaxies are arranged, forming what astronomers call a filamentary structure through the heart of the great nothing. This arrangement should be impossible. In normal regions of space, galaxies cluster around the densest areas, following the gravitational pull of dark matter. They form webs and sheets and clusters, but always following the underlying structure of matter distribution. Random chance cannot explain why 8 isolated galaxies would line up in such a precise formation. The tube stretches from one edge of the void to the other, like a cosmic highway, connecting distant shores of normal space. Each galaxy sits approximately 40 million light-years from its nearest neighbor along this invisible line. They are like streetlights on an impossibly long and empty road, marking a path through the darkness. This filamentary arrangement suggests that the void is not simply empty space. Something must have guided these galaxies into this formation. Some underlying structure, invisible to our telescopes, must exist within the emptiness. Dark matter, perhaps, or some other form of matter we have not yet learned to detect. Scientists have proposed that the tube represents a fossil from the early universe. During the first few 100 million years after the Big Bang, matter was distributed differently than it is today. Perhaps the void galaxies mark the location of an ancient filament of dark matter that once connected distant regions of space. As the universe expanded and evolved, most matter was pulled away from this region, leaving only this ghostly thread behind. The galaxies themselves show signs of unusual behavior that supports this theory. They are all moving along the same direction, as if following an invisible current. Their velocities are synchronized in a way that suggests they are all responding to the same gravitational influence, yet we cannot see what is pulling them. Spectroscopic analysis reveals that the void galaxies contain fewer heavy elements than galaxies of similar age in normal regions. This suggests they formed in an environment with less dense matter, supporting the idea that this region has been underdense for billions of years. They are time capsules, preserving conditions from an earlier epoch of cosmic evolution. The tube structure also explains why the void appears so empty from most viewing angles. If we look at the void from the side, we see it edge on, making it appear as a thin line of galaxies against the emptiness. From most other angles, the galaxies are aligned in such a way that they appear as a single point of light. This cosmic perspective trick makes the void seem even emptier than it actually is. But the true horror of the void becomes apparent when we measure how rapidly this emptiness is growing. The Boots void is not static. It is expanding faster than the universe itself, growing emptier with each passing million years. Imagine a balloon with a small hole that keeps getting bigger. As you inflate the balloon, the hole does not just maintain its size. It grows proportionally larger, consuming more and more of the balloon's surface. The Boots void behaves similarly, but instead of consuming rubber, it is consuming space where galaxies should exist. Measurements show that the void is expanding at a rate roughly 10% faster than the cosmic expansion caused by dark energy. This might seem like a small difference, but over cosmic timescales, it represents a fundamental departure from how space should behave. While normal regions of the universe expand due to dark energy, the void seems to be actively repelling matter, pushing galaxies away from its boundaries. This accelerated expansion creates what scientists call a void instability. Once a region becomes underdense, it becomes easier for matter to flow out of it rather than into it. Gravity, which normally pulls matter together, works in reverse at these scales. Instead of attracting nearby galaxies, the void's emptiness creates a gravitational gradient that pushes matter toward denser regions. Think of it like water flowing downhill. Normally, galaxies are attracted to areas of high matter density, like water flowing toward the bottom of a valley. But in the void, the emptiness creates an upward slope. Matter naturally flows away from the void toward regions where other galaxies already exist. This creates a feedback loop where emptiness breeds more emptiness. The mathematical models are disturbing. If current expansion rates continue, the Boots void will double in size within the next 5 billion years. By the time our sun burns out, this region of space will be twice as empty as it is today. The 8 survivor galaxies will be pushed further apart, their isolation becoming even more profound. But the expansion rate suggests something even more unsettling. The void is not just growing through normal cosmic expansion. Something is actively pushing matter away from this region. Dark energy, which causes the accelerated expansion of the entire universe, seems to be concentrated more heavily within the void. This creates a kind of cosmic vacuum cleaner effect, actively sucking matter density out of the region. Some theoretical physicists propose that we are witnessing the birth of a cosmic bubble of false vacuum. In this scenario, the laws of physics themselves might be different within the void. The vacuum state of space might be unstable, causing it to expand exponentially and push all matter toward the boundaries. If this theory is correct, the void represents a glimpse of what the entire universe might look like in the far future. The expansion also affects how we observe the void from Earth. Light from the few galaxies within the region is being redshifted more than expected, stretched toward longer wavelengths by the unusual expansion rate. This makes the void galaxies appear more distant and dimmer than they actually are. As the emptiness grows, it begins to affect the cosmic neighborhoods surrounding it. Around the edges of the Boots void, galaxies huddle together in unusually dense walls, as if fleeing from the emptiness within. These boundary regions contain 3 times more galaxies than normal areas of space. Imagine a crowd of people pressed against the walls of a room, all trying to stay as far as possible from something terrifying in the center. The galaxies surrounding the void behave exactly this way, clustering into dense filaments and sheets that form a kind of cosmic containment barrier. Scientists call these structures void walls, and they represent one of the most extreme examples of large-scale structure in the known universe. The walls stretch for hundreds of millions of light years, forming massive curtains of galaxies that separate the emptiness from normal space. Some individual wall segments contain more than 10,000 galaxies, packed into regions that would normally hold only 3,000. The density gradient is so sharp that you can actually see where normal space ends and the void begins. It is like standing at the edge of an ocean and watching where the water meets an empty beach. The transition happens over a relatively narrow zone, perhaps 20 million light-years wide. On one side, galaxies crowd together in normal cosmic abundance. On the other side, there is almost nothing. This sharp boundary violates our understanding of how matter should be distributed in the universe. Density variations should be smooth and gradual, following the gentle curves of gravitational influence. Instead, the void creates a cliff-like drop-off in galaxy density that suggests some violent process carved this hole in space. The void walls themselves show signs of unusual behavior. Galaxies within the walls are moving faster than expected, as if something is actively pushing them away from the void's interior. Their peculiar motions suggest that a repulsive force operates within the emptiness, creating what physicists call a negative pressure gradient. Computer simulations struggle to reproduce these wall structures through normal gravitational processes. Even when scientists start with the most extreme initial conditions possible, they cannot create void walls as dense as those observed around Boots. The walls seem to require some additional force or exotic form of matter to explain their existence. The walls also affect how light travels through this region of space. Photons from distant galaxies are deflected as they pass through the dense wall regions, creating subtle gravitational lensing effects. This makes galaxies behind the void appear slightly distorted, as if we are viewing them through cosmic funhouse mirrors. Most disturbing is what happens to galaxies that wander too close to the void boundary. Astronomical surveys have identified several galaxy groups that appear to be in the process of being absorbed by the emptiness. These falling galaxies show elongated shapes and unusual star formation patterns, as if they are being stretched and torn apart by tidal forces associated with the void. The walls represent a cosmic battle between emptiness and matter, with galaxies desperately clustering together to resist being swallowed by the growing hole in space. But to understand how such walls could form, we must examine the mysterious physics that allows matter to avoid certain regions of space for billions of years. The Boots void exists because matter has been fleeing this region of space for over 13 billion years, and the physics behind this cosmic abandonment reveals forces we barely understand. In the early universe, tiny quantum fluctuations created regions that were slightly more dense or slightly less dense than average. These fluctuations were incredibly small, representing differences of only 1 part in 100,000. Over time, gravity should have smoothed out these variations, pulling matter from less dense regions into more dense ones. But something went wrong in the region that would become the Boots void. Instead of smoothing out, the underdensity became more extreme. Matter did not just avoid this region, it actively fled from it, creating an emptiness that defies gravitational logic. Think of gravity like a landscape of hills and valleys. Normal regions of space have gentle slopes where matter rolls downhill toward areas of higher density. But the void region appears to have an uphill slope that pushes matter away. This creates what physicists call a repulsive gravitational field, though the mechanism behind this repulsion remains mysterious. One possibility involves dark energy, the mysterious force causing the accelerated expansion of the universe. Dark energy normally operates uniformly throughout space, but theoretical models suggest it could become concentrated in certain regions under specific conditions. If dark energy is more dense within the void, it would create a repulsive force strong enough to push normal matter away. Another explanation involves exotic matter states that might have existed in the early universe. During the first fractions of a second after the Big Bang, space itself might have undergone phase transitions similar to water freezing into ice. Some regions might have gotten stuck in a different phase, creating pockets of space with altered physical properties. The void might also represent a region where dark matter never properly condensed in the early universe. Dark matter provides the gravitational scaffolding upon which normal matter builds galaxies and larger structures. Without this scaffolding, normal matter would have no framework for clustering together. The region would remain forever empty, unable to form the dense concentrations necessary for galaxy formation. Measurements of the cosmic microwave background radiation support this theory. The ancient light from the Big Bang shows a cold spot in the direction of the Boots void, suggesting that this region has been underdense since the universe was only 380,000 years old. This cold spot represents the fossil evidence of the void's ancient origins. Computer simulations reveal that creating such extreme underdensity requires initial conditions that are statistically almost impossible. The probability of random fluctuations creating a void this large is less than 1 in 10 million. This suggests that the void might not be random at all, but rather the result of some systematic process that operated during the universe's infancy. Some theoretical physicists propose that cosmic inflation, the period of exponential expansion in the early universe, might have operated differently in this region. Inflation normally smooths out irregularities, but under certain conditions, it could amplify them instead, creating regions of extreme emptiness or extreme density. The physics becomes even stranger when we examine how this emptiness affects the fabric of spacetime itself. The Boots void does not just contain empty space, it actually changes the properties of space and time within its boundaries, creating a region where the normal rules of physics operate differently. Einstein's theory of general relativity tells us that matter and energy curve space-time, creating what we experience as gravity. Massive objects like stars and planets create depressions in space-time, while less massive regions create shallower curves. But what happens in a region with almost no matter at all? The void creates what physicists call a negative curvature in space-time. Instead of matter curving space inward, the absence of matter allows space to curve outward, creating a cosmic saddle shape. This unusual geometry affects how light travels through the region and how time itself flows within the emptiness. Light rays passing through the void follow paths that are subtly different from what we would expect in normal space. Instead of traveling in perfectly straight lines, photons curve slightly outward, following the unusual geometry of the underdense region. This creates a cosmic version of a diverging lens, causing light from distant galaxies to spread out more than it should. The effect is measurable but subtle. When astronomers observe galaxies located behind the void, they appear slightly dimmer and more spread out than expected. The void acts like a cosmic magnifying glass in reverse, making background objects appear smaller and fainter. This gravitational lensing signature provides direct evidence that the emptiness itself has gravitational effects. Time flows differently within the void compared to denser regions of space. According to general relativity, time runs faster in regions of weaker gravitational fields. Since the void contains far less matter than normal regions, clocks within the emptiness would tick slightly faster than clocks in galaxy-rich areas. This time dilation effect is incredibly small, only a few parts per billion, but it represents a fundamental difference in how space-time operates. The void also affects the propagation of gravitational waves. These ripples in space-time, first detected in 2015, travel at the speed of light through normal space. But when gravitational waves pass through the void, they experience subtle changes in amplitude and frequency due to the unusual space-time geometry. Future gravitational wave detectors might be able to use these effects to map the three-dimensional structure of cosmic voids. The underdense region creates what cosmologists call a gravitational Doppler effect. As light climbs out of the shallow gravitational well created by the void's boundaries, it loses energy and becomes redshifted. This effect is separate from the cosmological redshift caused by universal expansion, adding an additional layer of complexity to distance measurements. Some theoretical physicists propose that the void might contain exotic forms of matter that we cannot directly detect. These hypothetical particles would have negative energy density, creating repulsive gravitational effects that could explain the void's unusual properties. Such exotic matter remains purely theoretical, but its existence would fundamentally alter our understanding of what types of material can exist in the universe. The space-time geometry within the void also affects how cosmic rays propagate through the region. High-energy particles from distant sources follow curved paths through the unusual gravitational field, creating shadow zones where cosmic rays are deflected away from normal trajectories. These gravitational effects extend far beyond the void's visible boundaries, influencing the cosmic microwave background radiation across vast regions of sky. The Boots void casts a cold shadow across the cosmic microwave background radiation, the ancient light from the Big Bang, revealing how this emptiness has affected the universe since its earliest moments. The cosmic microwave background represents the oldest light in the universe, released when the cosmos was only 380,000 years old. This radiation should be nearly uniform across the sky, showing only tiny temperature variations that reflect the density fluctuations present in the early universe. But in the direction of the Boots void, there is a cold spot that should not exist. This cold spot spans several degrees across the sky, making it one of the largest, coherent features in the cosmic microwave background. The temperature difference is only about 30 millionths of a degree, but this tiny variation represents a profound anomaly in the universe's baby picture. It suggests that the void region was already significantly underdense when the universe was less than 1% of its current age. The cold spot forms through a process called the integrated Sachs-Wolf effect. As photons from the cosmic microwave background travel through regions of changing gravitational potential, they gain or lose energy. When light passes through a region that becomes less dense over time, it loses energy and becomes cooler. The Boots void has been emptying out for billions of years, creating exactly this effect. Think of it like a cosmic tax on light. As photons climb out of the void's evolving gravitational field, they pay an energy toll that leaves them slightly redder and cooler than when they entered. This process has been operating for over 13 billion years, gradually carving the cold signature into the background radiation. The size and intensity of the cold spot provide crucial information about the void's history. Computer models can work backward from the observed temperature depression to determine how the emptiness evolved over cosmic time. These calculations suggest that the void began as a relatively modest underdensity in the early universe and has been growing emptier ever since. But the cold spot reveals an additional mystery. According to standard cosmological models, the temperature depression should be even larger than what we observe. The measured cold spot is only about half as intense as theoretical predictions suggest. This discrepancy hints that our understanding of how voids evolve might be incomplete, or that exotic physics operates within these empty regions. Some cosmologists propose that the cold spot signature has been partially erased by secondary effects. As the cosmic microwave background photons travel through the void, they might interact with hot gas or energetic processes that add heat back to the radiation. This could explain why the cold spot appears weaker than expected. The angular size of the cold spot also provides information about the void's three-dimensional structure. By measuring how the temperature depression varies across different directions, astronomers can map the void's shape and orientation relative to our line of sight. These measurements confirm that we are viewing the void nearly face-on, seeing its full 300 million light-year extent. Other cosmic voids create their own cold spots in the microwave background, but none are as large or as well-defined as the Boots signature. This supports the idea that the Boots void represents an extreme example of cosmic underdensity, far beyond what normal statistical fluctuations should produce. The cold spot also affects how we measure fundamental cosmological parameters. The temperature pattern provides independent evidence for dark energy and helps constrain models of cosmic inflation. This ancient signature raises disturbing questions about whether the void represents a single enormous hole in space or something even stranger. Recent deep surveys reveal that the Boots void might not be a single empty region, but rather 3 or 4 smaller voids that have merged together into one massive hole in space. High-resolution galaxy surveys using the Sloan Digital Sky Survey and other major telescopes have mapped the void's internal structure in unprecedented detail. Instead of finding uniform emptiness, astronomers discovered evidence of multiple overlapping underdense regions, each with its own distinct properties and evolutionary history. Picture three soap bubbles floating in water that gradually drift together and merge into one larger bubble. The Boots void appears to have formed through a similar process, with smaller voids combining over billions of years to create the enormous emptiness we observe today. Each component void contributes its own characteristics to the final merged structure. The evidence for multiple voids comes from the peculiar distribution of the few galaxies found within the region. Instead of being randomly scattered throughout the emptiness, these galaxies are clustered into small groups that appear to mark the boundaries between the original component voids. The 8 bright galaxies form a tube-like structure that might represent the interface where two large voids have merged together. Computer simulations support this merger scenario. Models that start with multiple, smaller, underdense regions in the early universe can reproduce the observed structure of the Boots void more accurately than simulations that assume a single, large, empty region. The merger process naturally explains the void's elongated shape and the peculiar arrangement of galaxies within it. Each component void appears to have formed at a slightly different time in cosmic history. Spectroscopic measurements of the few galaxies within the region show subtle differences in their stellar populations and chemical compositions. These differences suggest that different parts of the void have been empty for different lengths of time, supporting the merger hypothesis. The northern section of the void contains galaxies that are slightly older and more metal-poor than those in the southern section. This gradient suggests that the northern void formed earlier and has been empty longer, allowing less time for star formation and chemical enrichment in the galaxies that managed to survive there. The merger process also explains the void's unusual expansion rate. When smaller voids combine, their gravitational effects add together, creating a larger region with stronger repulsive properties. The merged void expands faster than any of its component parts would individually, accelerating the process of cosmic evacuation. Theoretical models predict that void mergers should be relatively common in the universe's later stages. As cosmic expansion continues and dark energy becomes more dominant, smaller voids should naturally grow and combine into larger empty regions. The Boots void might represent a preview of what much of the universe will look like in the far future. The merger scenario also helps explain why the void is so much larger than statistical models predict for random density fluctuations. While the probability of forming one void this large is incredibly small, the probability of forming several smaller voids that subsequently merge is much higher. The observed structure might result from a series of unlikely but not impossible events. Deep radio surveys have revealed additional evidence for the merger hypothesis. The few galaxies within the void show unusual radio emission patterns that suggest they have been affected by multiple episodes of environmental change. These galaxies bear the scars of living through several void merger events over billions of years. But regardless of whether the void formed as one massive hole or several merged monsters, its existence points to forces that operate on scales beyond normal cosmic evolution. The Boots void may serve as a natural laboratory where dark energy operates more powerfully than anywhere else in the universe, revealing clues about the mysterious force driving cosmic acceleration. Dark energy makes up 68% of the universe, yet we understand almost nothing about its nature or properties. We know it causes space itself to expand at an accelerating rate, but we cannot detect it directly or explain why it exists. The Boots void offers a unique opportunity to study dark energy in isolation, removed from the complicating effects of matter and radiation. In normal regions of space, dark energy's effects are subtle and difficult to measure. The presence of galaxies, dark matter, and other forms of energy creates a complex gravitational environment where dark energy's influence is masked by stronger forces. But within the void, these masking effects are almost entirely absent. The emptiness creates a clean environment where dark energy's properties become more apparent. Measurements show that space within the void is expanding faster than the cosmic average. This accelerated expansion suggests that dark energy might be more concentrated or more active within underdense regions. Think of dark energy like a gas that becomes more potent when it has more room to operate. In the compressed environment around galaxies, dark energy's effects are suppressed. In the vast emptiness of the void, it can exert its full influence. Some theoretical models propose that dark energy is not actually constant throughout space and time. These quintessence models suggest that dark energy's strength varies depending on local conditions, becoming stronger in regions with lower matter density. The Boots void provides a perfect testing ground for these theories, offering an environment where matter density is essentially zero. The void's expansion rate also provides insights into dark energy's equation of state, a fundamental property that determines how the force behaves under different conditions. By measuring how the void grows over time and comparing this to theoretical predictions, cosmologists can constrain models of dark energy and rule out certain exotic alternatives. Temperature measurements of the cosmic microwave background in the void's direction support the idea that dark energy operates differently there. The observed cold spot is consistent with enhanced dark energy activity that has been actively removing matter from the region for billions of years. This creates a feedback loop where emptiness enhances dark energy's effects, which in turn create more emptiness. The void might also help resolve one of cosmology's biggest mysteries: the cosmic coincidence problem. Why does dark energy's density appear to be precisely tuned to become dominant at the current epoch in cosmic history? The void's properties suggest that dark energy's effects depend on the matter environment, potentially providing a natural explanation for this apparent fine-tuning. Future space-based telescopes will use the void as a dark energy laboratory. By monitoring how the void's boundaries evolve over time and measuring the peculiar velocities of galaxies near the edges, scientists can map dark energy's influence with unprecedented precision. These observations might finally reveal whether dark energy is truly constant or varies throughout space and time. The void also offers insights into the connection between dark energy and cosmic inflation, the period of exponential expansion in the early universe. Some models suggest that dark energy is a remnant of the inflaton field that drove cosmic inflation. If so, the void might preserve signatures of that ancient epoch, offering a window into the universe's first moments. But the void's relationship to dark energy raises disturbing questions about the universe's ultimate fate and what this emptiness tells us about the cosmos we inhabit. This extraordinary emptiness demonstrates that our universe contains regions where the normal rules break down, where forces we barely understand shape reality on scales that dwarf human comprehension. As we peer deeper into the Boots void, we discover that the cosmos is far stranger and more mysterious than we ever imagined. At the boundaries of the Boots void, gravity itself behaves differently, creating a cosmic desert where matter flows outward like water draining from a broken dam. Normal gravity pulls matter together, creating the cosmic web of galaxies and dark matter filaments that we observe throughout most of the universe. But at the void's edges, gravity operates in reverse. Instead of attracting matter, the combined gravitational effect of the surrounding emptiness creates a repulsive force that pushes galaxies away from the void's interior. This gravitational inversion happens because of what physicists call the Birkhoff theorem in reverse. In regions of extreme underdensity, the absence of matter creates a negative gravitational potential that acts like an anti-gravity field. Galaxies near the void's boundaries experience a force that pulls them toward regions of higher matter density, effectively draining material from the empty region. Measurements of galaxy velocities near the void confirm this unusual gravitational behavior. Galaxies located within 50 million light-years of the void's edge are moving away from the empty region at speeds up to 600 miles per second faster than cosmic expansion would predict. These peculiar velocities indicate that something is actively pushing matter away from the void. The effect becomes stronger closer to the void's center. Computer simulations show that any galaxy unlucky enough to wander into the void's interior would be accelerated outward by these gravitational forces, unable to maintain a stable orbit within the empty region. The void acts like a cosmic vacuum cleaner in reverse, actively expelling any matter that dares to enter its domain. This gravitational behavior explains why the few galaxies that do exist within the void are so peculiar. They represent the survivors of a cosmic evacuation process that has been operating for billions of years. These galaxies managed to form in the early universe before the void's repulsive effects became dominant, but they have been slowly starved of new material ever since. The repulsive gravitational field also affects how dark matter behaves in the region. While we cannot directly observe dark matter, computer simulations suggest that dark matter particles should also be expelled from the void by the same gravitational forces affecting normal matter. This creates a region where even the invisible scaffolding of cosmic structure has been stripped away. The void's gravitational desert extends far beyond its visible boundaries. Surveys show that galaxy formation rates are suppressed in a zone extending up to 100 million light-years beyond the void's edge. This gravitational shadow affects how matter accumulates throughout a vast region of space, creating underdensities that cascade outward from the central emptiness. Temperature measurements provide additional evidence for unusual gravitational effects. Gas that falls toward the void's boundaries should heat up as it accelerates under gravitational influence. But observations show that intergalactic gas near the void is actually cooler than expected, suggesting that the gravitational field is doing negative work on the material, cooling it rather than heating it. The repulsive gravity also affects how cosmic rays propagate through the region. High-energy particles from distant sources are deflected away from the void, creating a cosmic ray shadow that extends across multiple degrees of sky. This effect provides another independent confirmation that the void's gravitational field operates differently from normal space. Some theoretical physicists propose that the void's unusual gravity might be evidence for modified theories of gravitation. While Einstein's general relativity works well in regions of normal matter density, it might require modifications in extreme environments like cosmic voids. The Boots void could serve as a testing ground for these alternative theories. The gravitational desert creates conditions that challenge our understanding of how cosmic structure should evolve, raising fundamental questions about the cosmic web itself. The Boots void represents a catastrophic failure of the cosmic web, the largest structure in the universe, revealing that our models of how matter organizes on cosmic scales are fundamentally incomplete. The cosmic web is the scaffold upon which all cosmic structure is built. Dark matter forms filaments, connecting galaxy clusters, creating a three-dimensional network that spans the observable universe. Galaxies form where these filaments intersect, while large empty regions called voids exist in the spaces between filaments. This web-like structure should be continuous and connected throughout space, but the Boots void breaks this fundamental rule. It represents a massive hole in the cosmic web where no filaments exist to connect distant regions of space. Imagine a spider web with a section completely torn away, leaving loose strands hanging in empty air. The void creates exactly this kind of topological defect in the universe's largest structure. Computer simulations of cosmic structure formation cannot reproduce voids as large and empty as Boots using standard models of dark matter and gravity. Even when scientists start simulations with the most extreme initial conditions possible, they cannot create such massive holes in the cosmic web. The void's existence suggests that our understanding of how structure forms in the universe is missing crucial components. The web's failure has cascading effects throughout the surrounding region. Filaments that should connect to the void's far side are truncated, ending abruptly at the void's boundaries. This creates orphan galaxy clusters that lack the normal cosmic context, isolated islands of matter surrounded by abnormal emptiness. Galaxy formation rates are suppressed throughout a vast region surrounding the void, extending the web's failure far beyond the empty region itself. New galaxies cannot form without the gravitational framework provided by dark matter filaments, so the web's absence creates a zone of cosmic sterility that encompasses hundreds of millions of light-years. The void also disrupts the normal flow of matter through the cosmic web. In healthy regions of the web, matter streams along filaments toward intersection points where galaxy clusters form. But the void creates a kind of cosmic sinkhole that interrupts these flows, causing matter to pile up at the void's boundaries rather than following its normal trajectory through the web structure. Measurements of the cosmic microwave background reveal that the Webb's failure extends back to the universe's earliest epochs. The temperature patterns in the ancient radiation show that this region lacked the normal network of density fluctuations that should have provided the seeds for web formation. The cosmic web was broken here from the very beginning. Some cosmologists propose that the void represents a cosmic domain boundary where different regions of spacetime with incompatible properties meet. During cosmic inflation in the early universe, different regions might have undergone slightly different expansion histories, creating boundaries where the cosmic web cannot properly connect. The web's failure also affects how information propagates through the universe. In normal regions, gravitational influences travel along the web's filaments, allowing distant parts of the universe to remain causally connected. But the void creates a communication gap, where gravitational information cannot flow, isolating the regions on either side of the emptiness. Advanced statistical analysis reveals that the void's impact on the cosmic web extends across scales ranging from individual galaxies to superclusters. The web's topology is fundamentally altered throughout a region, encompassing nearly 1 billion cubic light-years of space, making this the largest known structural defect in the universe. The broken web creates what cosmologists call frustrated cosmic evolution, where the normal processes of structure formation are prevented from operating efficiently. This structural failure has profound implications for how dark matter, the invisible foundation of cosmic structure, is distributed throughout this region of space. The Boots void challenges everything we know about dark matter distribution, suggesting that the invisible foundation of cosmic structure might be arranged in ways that violate our most basic theoretical assumptions. Dark matter makes up 85% of all matter in the universe, yet it interacts only through gravity, making it invisible to direct observation. We infer its presence through its gravitational effects on normal matter and through computer simulations that require dark matter to explain how galaxies and larger structures form. According to these models, dark matter should be distributed relatively smoothly throughout space, with concentrations marking the locations where galaxies eventually form. But the Boots void appears to contain almost no dark matter at all. Gravitational lensing measurements, which reveal dark matter's presence through its bending of light from background galaxies, show that the void region has a dark matter density less than 10% of the cosmic average. This represents one of the most extreme dark matter deficits ever detected in the universe. The absence of dark matter creates a profound puzzle. In standard cosmological models, dark matter provides the gravitational scaffolding that allows normal matter to clump together and form galaxies. Without this invisible framework, galaxy formation should be impossible. Yet the void contains 8 survivor galaxies that somehow manage to form despite the lack of dark matter support. Computer simulations struggle to explain how such extreme dark matter underdensity could develop through normal gravitational processes. Even in the most underdense regions predicted by theoretical models, dark matter should still maintain at least 30% of the cosmic average density. The void's dark matter content is far below this minimum threshold. Some physicists propose that the void might contain a different type of dark matter with unusual properties. Instead of the standard cold dark matter that moves slowly and clumps together gravitationally, the void might be filled with warm or hot dark matter that moves too quickly to form stable concentrations. This exotic dark matter would be effectively invisible to our current detection methods. Another possibility involves dark matter self-interactions. Most dark matter models assume that dark matter particles only interact through gravity, but some theories propose that dark matter can interact with itself through unknown forces. In regions where dark matter density becomes very low, these self-interactions might cause the remaining dark matter to annihilate or decay, creating a self-reinforcing feedback loop that empties the region completely. The void's dark matter deficit also affects how we interpret gravitational lensing observations throughout the surrounding region. Light from distant galaxies that passes near the void should be deflected less than expected due to the reduced gravitational influence. This creates systematic errors in distance measurements and mass estimates for background objects. Measurements of galaxy rotation curves within the void provide additional clues about dark matter's behavior. The few galaxies that exist in the region show unusual rotation patterns that suggest they contain less dark matter than similar galaxies in normal environments. This supports the idea that dark matter has been actively removed from the entire region. Some cosmologists suggest that the void might represent evidence for alternative theories of gravity that do not require dark matter at all. Modified gravity theories like MOND, modified Newtonian dynamics, predict that gravitational effects should be different in extremely low-density environments. The void could serve as a natural laboratory for testing these alternative theories. The dark matter mystery deepens when we consider that the void's few galaxies show signs of having formed through normal processes despite their dark matter-poor environment. Their stellar populations and chemical compositions are consistent with standard galaxy formation models, yet they exist in a region where such formation should be impossible. Advanced computer simulations using different dark matter models all fail to reproduce the void's extreme properties, suggesting that our understanding of dark matter's behavior in underdense environments is fundamentally flawed. This dark matter enigma raises questions about how normal matter flows through regions of extreme cosmic underdensity. Matter flows around the Boots void like cosmic rivers flowing around a massive stone, creating streaming patterns that reveal the invisible forces shaping large-scale structure throughout the universe. Galaxy surveys show that matter does not simply avoid the void randomly. Instead, galaxies and dark matter form coherent streams that flow around the empty region in predictable patterns. These cosmic currents follow paths determined by the void's gravitational influence, creating a hydrodynamic flow pattern on scales of hundreds of millions of light-years. The largest of these streams is the Perseus-Pisces supercluster chain, a massive river of galaxies that curves around the void's northern boundary. This supercluster chain contains thousands of galaxies flowing in the same direction, all apparently deflected by their gravitational interaction with the empty region. The stream maintains its coherence across distances that span nearly 500 million light-years. Computer simulations reveal that these matter streams are remarkably stable structures. Once established, they persist for billions of years, continuously channeling galaxies away from the void and toward regions of higher density. The streams act like cosmic highways, providing preferential routes for matter transport throughout this region of the universe. The flow patterns also explain why certain directions around the void contain many more galaxies than others. Matter tends to accumulate where multiple streams converge, creating the dense void walls observed at specific locations around the empty region's boundary. These convergence zones represent cosmic river deltas, where multiple currents deposit their galactic cargo. Velocity measurements confirm that galaxies within these streams are moving faster than cosmic expansion would predict. The peculiar velocities can exceed 1,000 miles per second, indicating that powerful gravitational forces are actively driving the flow patterns. These velocities are among the largest coherent motions ever detected in the universe. The streaming also affects how galaxies evolve within the flows. Galaxies caught in the cosmic currents experience ram pressure as they move through intergalactic gas, stripping away their outer material and altering their star formation rates. Many stream galaxies show evidence of recent tidal interactions, suggesting that the flowing environment creates more frequent galaxy encounters. Temperature maps of the cosmic microwave background show additional evidence for these matter flows. The ancient radiation exhibits subtle Doppler shifts in directions corresponding to the major stream locations, indicating that these flow patterns have been operating since the early universe. The streams represent some of the oldest large-scale structures in the cosmos. The void's gravitational influence extends far beyond its visible boundaries, affecting matter flows across a region spanning more than 1 billion light-years. This gravitational basin channels matter away from a vast volume of space, contributing to underdensities that extend far beyond the main empty region. Some streams show evidence of having been deflected multiple times by their interaction with the void's evolving gravitational field. As the void has grown over cosmic time, it has gradually altered the trajectories of nearby matter flows, creating curved paths that record the history of the region's gravitational evolution. The streaming patterns also provide insights into the three-dimensional structure of dark matter in the region. While dark matter cannot be directly observed, its gravitational effects on galaxy streams reveal where invisible matter concentrations exist. These measurements show that dark matter flows follow the same general patterns as normal matter, but with subtle differences that reflect dark matter's unique properties. Advanced statistical analysis reveals that the void's matter streams are connected to similar flow patterns throughout the observable universe. The Boots region appears to be part of a global network of cosmic currents that transport matter between different large-scale structures. These flowing rivers of galaxies carry with them clues about what the universe might look like in the distant future. The Boots void offers a terrifying preview of what the entire universe might look like trillions of years from now, when dark energy has stretched space so much that every galaxy becomes an isolated island in an ocean of emptiness. Current cosmological models predict that the universe's expansion will continue accelerating indefinitely due to dark energy's influence. Over the next 100 billion years, galaxies outside our local group will be carried away by cosmic expansion until they disappear beyond our observable horizon. The night sky will gradually become darker as distant galaxies fade from view, leaving only the few gravitationally bound systems in our immediate cosmic neighborhood. But the Boots void shows us what comes after even this lonely future. In the void's extreme isolation, we see what happens when cosmic expansion progresses to its ultimate conclusion. The few survivor galaxies in the void are separated by distances so vast that inhabitants of one galaxy would be completely unaware that any others exist. Each galaxy becomes a cosmic hermit, alone, in an apparently infinite darkness. The void galaxies show signs of premature aging that might foreshadow the fate of all galaxies in the far future. Cut off from external sources of fresh material, they consume their gas supplies at unusually slow rates. Their star formation has nearly ceased, and their stellar populations are dominated by old red stars. These galaxies represent cosmic retirees, systems that have exhausted their ability to create new generations of stars. Computer simulations that extrapolate current expansion rates suggest that the entire observable universe will resemble the Boots void within 10 trillion years. By that time, cosmic expansion will have stretched space so much that galaxy densities throughout the universe will match those currently seen only within the void. Every galaxy will experience the same profound isolation that currently affects only the void's inhabitants. The void also demonstrates how cosmic expansion affects the evolution of life and intelligence. Any civilization that develops within the void would face unique challenges in understanding their cosmic environment. Their night sky would appear almost completely empty, providing no evidence for the existence of other galaxies, or even for cosmic expansion itself. They might conclude that their galaxy represents the entire universe. This cosmic loneliness has profound implications for the development of science and philosophy within isolated galaxies. The cosmic microwave background radiation would still be detectable, but without other galaxies for reference, void civilizations might struggle to interpret its meaning. They would lack the observational context necessary to discover fundamental cosmological principles. The void's expansion rate suggests that this isolation will only increase over time. Even the 8 survivor galaxies are gradually being pushed further apart by the accelerating expansion of space within the empty region. Eventually, each void galaxy will lose sight of all the others, becoming truly alone in the cosmic darkness. Temperature measurements show that space within the void is already approaching the ultimate cosmic cold. With so little matter to provide heating through gravitational interactions, the void represents one of the coldest regions in the current universe. This extreme cold previews the thermal state that will eventually characterize all of space when cosmic expansion has diluted matter to near zero densities. The void also demonstrates how the second law of thermodynamics operates on cosmic scales. The emptiness represents a state of maximum entropy for this region of space, where matter has been dispersed as evenly as possible given the gravitational constraints. This maximum entropy state might represent the ultimate fate of the entire universe. Some theoretical physicists propose that the void's extreme isolation might actually protect its galaxies from certain cosmic catastrophes. In the far future, when proton decay begins to dismantle normal matter. The void's isolation might shield its contents from this universal dissolution, allowing matter to persist longer than it would in denser environments. But this preview of cosmic loneliness raises disturbing questions about whether the void represents our universe's destiny or an anomaly that tells us something fundamental about cosmic expansion itself. The Boots void serves as a cosmic measuring stick that reveals fundamental properties of the universe's expansion, providing unique insights into dark energy and the future of cosmic evolution. Astronomers use various methods to measure how fast the universe is expanding, but most techniques rely on observations of galaxies and other bright objects. The void offers something different, a way to measure expansion using emptiness itself. By tracking how the void's boundaries evolve over time, cosmologists can directly observe cosmic expansion in action. The void's expansion rate differs from the cosmic average in subtle but measurable ways. While the overall universe expands at a rate described by the Hubble constant, the void expands approximately 10% faster. This difference provides crucial information about how dark energy operates in different environments and helps constrain theoretical models of cosmic acceleration. Measurements of the void's angular size at different cosmic epochs allow astronomers to trace the history of cosmic expansion with unprecedented precision. Light from the few galaxies within the void carries information about the region's size at various times in the past. By comparing these historical measurements to current observations, scientists can reconstruct how expansion rates have changed over billions of years. The void also provides a clean laboratory for testing the relationship between matter density and expansion rate. In normal regions of space, the complex gravitational interactions between galaxies, dark matter, and cosmic radiation make it difficult to isolate dark energy's effects. The void's extreme emptiness eliminates most of these complications, allowing for more precise measurements of how dark energy drives cosmic acceleration. Redshift measurements of the void galaxies reveal subtle departures from standard expansion predictions. These galaxies show slightly higher redshifts than expected based on their distances, indicating that light from these sources has been stretched by enhanced expansion within the void. This effect provides direct observational evidence that cosmic expansion operates differently in underdense regions. The void's contribution to Hubble constant measurements helps resolve discrepancies between different observational techniques. Recent measurements of the cosmic expansion rate using different methods have yielded conflicting results, creating what cosmologists call the Hubble tension. The void's unique expansion properties might help explain these discrepancies and point toward a resolution of this fundamental problem. Temperature fluctuations in the cosmic microwave background toward the void direction provide additional constraints on expansion models. The observed cold spot is sensitive to how expansion rates have evolved over cosmic time, offering an independent check on other expansion measurements. These temperature measurements extend our knowledge of cosmic expansion back to when the universe was less than 1% of its current age. The void's expansion also affects measurements of cosmic distances throughout the surrounding region. The enhanced expansion within the void creates systematic errors in standard distance measurement techniques, requiring corrections that depend on detailed models of how expansion varies with local density. These corrections have implications for measuring distances to supernovae and other cosmic distance indicators. Computer simulations that match the void's observed expansion properties require specific combinations of dark energy parameters and matter densities. These requirements provide tight constraints on cosmological models and help rule out certain exotic theories of cosmic acceleration. The void serves as a cosmic laboratory where theoretical predictions can be tested against detailed observations. The expansion measurements also reveal information about the void's internal structure and evolution. Different parts of the void expand at slightly different rates, reflecting variations in local matter density and gravitational influence. These differential expansion rates provide insights into how the void formed and how it will continue to evolve. Advanced statistical techniques applied to the void's expansion data help improve our understanding of cosmic parameter uncertainties. The void represents an independent measurement of cosmic expansion that can be combined with other observations to reduce systematic errors and improve the precision of fundamental cosmological parameters. These expansion measurements raise profound questions about whether the void represents a preview of cosmic acceleration or evidence for hidden forms of matter and energy. Deep within the Boots void, cutting-edge telescopes are beginning to detect faint traces of matter that might reveal entirely new categories of cosmic objects, hidden forms of energy, or even evidence for physics beyond our current understanding. The void was originally defined by the absence of bright galaxies, but modern instruments with unprecedented sensitivity are discovering that empty space contains more than initially apparent. Ultra-deep surveys using the Hubble Space Telescope and ground-based observatories have revealed extremely faint objects scattered throughout the void that were invisible to earlier generations of telescopes. These hidden objects include dwarf galaxies so dim that they contain fewer stars than a typical globular cluster. Some of these ultra-faint systems are so sparse that individual stars are separated by distances comparable to those between neighboring star systems. They represent a completely different category of galaxy, one that exists on the border between bound gravitational systems and dispersed stellar associations. Radio surveys have detected mysterious emissions from within the void that cannot be attributed to known sources. These radio signals are extremely weak and appear to come from large, diffuse regions rather than point sources. Some astronomers propose that these emissions might originate from previously unknown forms of cosmic plasma or exotic matter states that can only exist in extremely underdense environments. Infrared observations reveal warm dust scattered throughout the void that glows too faintly to be detected at visible wavelengths. This dust appears to be organized into filamentary structures that span millions of light years, suggesting that some form of large-scale organization exists even within the apparent emptiness. The dust's temperature and distribution patterns provide clues about energy sources that remain unidentified. Gravitational wave detectors have begun searching for signals that might originate from within the void. While no confirmed detections have been made, theoretical models suggest that exotic objects like primordial black holes or cosmic strings might be more common in underdense regions. The void's unique environment might preserve relics from the early universe that have been destroyed elsewhere by galactic interactions. X-ray observations have detected extremely hot, tenuous gas distributed throughout parts of the void. This gas is hundreds of times hotter than typical intergalactic medium and appears to be heated by unknown energy sources. The gas's temperature and distribution suggest that energetic processes operate within the void despite the apparent absence of conventional energy sources like star formation or black hole accretion. Dark matter detection experiments are beginning to focus on void regions as potential sources of exotic signals. Some theoretical models predict that dark matter self-interactions might be enhanced in extremely underdense environments, potentially creating detectable signatures that would be overwhelmed by background effects in normal regions of space. The void might serve as a natural dark matter laboratory. Neutrino observatories are monitoring the void direction for unusual signals that might indicate the presence of exotic matter or energy. While neutrinos interact weakly with normal matter, they might interact more strongly with hypothetical forms of dark sector matter that could be concentrated within void regions. Any detected excess of neutrinos from the void direction would provide evidence for physics beyond the standard model. Cosmic ray studies have identified subtle anisotropies in high-energy particle arrival directions that might be associated with the void's gravitational influence. These particles, some carrying energies exceeding those achievable in terrestrial accelerators, might be deflected by invisible matter concentrations within the void or accelerated by unknown energy sources. Measurements of the cosmic microwave background are reaching sufficient sensitivity to detect secondary effects from matter within the void. These might include inverse Compton scattering from hot electrons, gravitational lensing from compact objects, or other subtle signatures that require extremely precise measurements to detect. Advanced computer simulations predict that the void might contain significant amounts of matter in forms that current observations cannot detect. This hidden matter might include failed galaxies that never formed stars, populations of isolated brown dwarfs, or even exotic objects like dark stars powered by dark matter annihilation. The search for hidden matter within the void represents one of the most challenging observational programs in modern astronomy, pushing current technology to its absolute limits and driving the development of next-generation instruments. The discovery of the Boots void sparked a systematic search for similar structures throughout the universe, revealing that cosmic voids represent a fundamental component of large-scale structure that was previously underappreciated. Since the Boots void's discovery, astronomers have cataloged hundreds of other cosmic voids with varying sizes, shapes, and properties. These voids form a hierarchy of emptiness, ranging from relatively small regions only 50 million light-years across to massive supervoids that rival Boots in their scope and impact. Together, they demonstrate that cosmic voids are not rare anomalies, but rather common features of cosmic architecture. The largest known void, recently discovered in the constellation Eridanus, spans nearly 2 billion light-years across and contains even fewer galaxies per unit volume than Boots. This supervoid is so large that light requires 2 billion years to cross from one side to the other, making it comparable in size to the largest known structures in the universe. Its discovery suggests that cosmic emptiness can be organized on scales that approach the universe's largest dimensions. Each void in this cosmic family has unique characteristics that provide insights into different aspects of cosmic evolution. The Sculptor void shows evidence of recent galaxy formation within its boundaries, suggesting that some voids can be gradually filled in over cosmic time. The Capricornus void contains an unusually high number of dwarf galaxies, indicating that small-scale structure formation might be enhanced in certain underdense environments. Statistical analysis of void properties reveals that they follow predictable scaling relationships. Larger voids tend to be emptier, expanding faster, and more spherical in shape. These relationships provide crucial tests for theories of cosmic structure formation and help constrain models of how voids evolve over cosmic time. The spatial distribution of voids throughout the observable universe shows that they are not randomly scattered, but instead form coherent patterns. Voids tend to be connected to each other through tendrils of reduced galaxy density, creating a network of emptiness that complements the cosmic web of matter. This void network represents the negative space of cosmic structure, equally important for understanding how matter is organized on the largest scales. Comparative studies reveal that void properties depend on the cosmic environment in which they form. Voids located in regions of higher overall density tend to be smaller and less empty, while those in already underdense regions can grow to enormous sizes like Boots. This environmental dependence provides insights into the feedback mechanisms that control void evolution. Temperature measurements of the cosmic microwave background reveal that most large voids create detectable cold spots, though none as prominent as the Boots signature. These cold spots form a pattern across the sky that traces the void network and provides information about how these structures affect the universe's thermal history. Computer simulations that include realistic populations of cosmic voids can reproduce the observed large-scale structure of the universe much more accurately than simulations that focus only on matter concentrations. Voids play an active role in cosmic evolution, channeling matter flows and affecting galaxy formation across vast regions of space. The void family also includes structures with exotic properties that challenge our understanding of cosmic evolution. Some voids show evidence of internal rotation, spinning slowly around their central axes over hundreds of millions of years. Others contain unusual concentrations of dark matter that seem to contradict their apparent emptiness. These anomalous voids might preserve signatures of exotic physics from the early universe. Recent discoveries have identified void-in-void structures, where smaller empty regions exist within larger voids, creating nested hierarchies of emptiness. These structures suggest that void formation operates on multiple scales simultaneously, and that the processes creating cosmic emptiness are more complex than previously recognized. The void family continues to grow as more sensitive surveys detect smaller and more distant empty regions. Future space-based telescopes will extend void catalogs to higher redshifts, allowing astronomers to study how void properties have evolved over cosmic time and providing crucial tests for cosmological models. Comparative analysis of the void family provides the statistical power necessary to distinguish between different theories of cosmic structure formation and to identify the physical processes responsible for creating such massive regions. Of emptiness, the Boots void and other cosmic voids might preserve direct evidence from cosmic inflation, the period of exponential expansion that occurred during the universe's first fraction of a second, offering our best opportunity to understand the physics of creation itself. Cosmic inflation theory proposes that the universe underwent a brief period of exponential expansion when it was less than a trillionth of a trillionth of a trillionth of a second old. During this inflationary epoch, quantum fluctuations in the vacuum were stretched to cosmic scales, creating the density variations that eventually became galaxies, clusters, and voids. The largest cosmic voids might represent direct fossils from this primordial period. The size distribution of cosmic voids provides crucial tests for different models of cosmic inflation. Various inflation theories predict different patterns of density fluctuations, which should be reflected in the statistical properties of void populations. The existence of supervoids like Boots places constraints on the energy scale and duration of cosmic inflation, ruling out certain theoretical models while supporting others. Temperature fluctuations in the cosmic microwave background toward void regions preserve information about the quantum state of the universe during inflation. The observed cold spots associated with large voids are consistent with specific predictions of inflation theory, providing independent confirmation that this process actually occurred. The amplitude and angular scale of these temperature variations match theoretical expectations for inflation-generated fluctuations. Some inflation models predict that the process should create isolated regions with different physical properties, including different values of fundamental constants or even different particle physics. Large cosmic voids might represent boundaries between such regions, where matter with incompatible properties cannot coexist. The extreme emptiness of voids like Boots could result from this fundamental incompatibility. The void's impact on cosmic microwave background polarization provides additional signatures of inflationary physics. Inflation should have generated primordial gravitational waves that left characteristic imprints on the polarization patterns of the ancient radiation. Voids affect how this polarization signal propagates to Earth, creating opportunities to detect inflationary gravitational waves that would otherwise be too weak to observe. Advanced theoretical models suggest that cosmic inflation might have operated differently in various regions of space, creating a multiverse of domains with different properties. The boundaries between these domains would appear as supervoids in our observable universe. If correct, the Boots void might represent a window into a neighboring universe with different physical laws. The void's expansion properties provide insights into the equation of state during cosmic inflation. Different inflation models predict different relationships between pressure and energy density during the inflationary epoch. By measuring how voids expand and comparing this to theoretical predictions, cosmologists can constrain the physics of the inflaton field that drove cosmic expansion. Quantum field theory calculations suggest that vacuum fluctuations during inflation should have created not only density variations, but also fluctuations in the vacuum energy itself. These quantum vacuum fluctuations might be preserved as dark energy concentrations within cosmic voids, providing a direct link between inflation and the current cosmic acceleration. Non-Gaussianity measurements of cosmic structure provide another connection to inflationary physics. Simple inflation models predict that density fluctuations should follow Gaussian statistics, but more complex models predict departures from this pattern. The statistical properties of void populations, including their shapes and clustering patterns, provide sensitive tests for non-Gaussian signatures from inflation. Recent theoretical work suggests that cosmic voids might preserve information about the quantum entanglement structure of the early universe. During inflation, quantum correlations were stretched across cosmic distances, potentially creating long-range entanglement patterns that influence how matter is distributed within and around cosmic voids. The void's extreme properties might also provide evidence for eternal inflation, the idea that cosmic inflation continues forever in some regions while ending in others. Our observable universe might represent a finite bubble within an eternally inflating multiverse, with supervoids marking the boundaries where inflation ended at different times. Future gravitational wave observatories might detect primordial signals generated during cosmic inflation by monitoring how these waves interact with cosmic void structures. The voids could serve as natural gravitational wave lenses, amplifying or focusing primordial signals in ways that make them detectable with current technology. These connections between cosmic voids and inflationary physics represent some of the most direct observational tests available for understanding the universe's ultimate origins. The existence of cosmic voids, like boots, forces scientists to reconsider fundamental assumptions about how the universe evolved from a smooth, hot plasma into the complex web of galaxies and empty regions we observe today. Standard models of cosmic structure formation begin with tiny density fluctuations present when the universe was only 380,000 years old. These fluctuations, preserved in the cosmic microwave background radiation, should have grown over time through gravitational attraction, creating the galaxies and larger structures we observe today. But this process should also smooth out large-scale irregularities, making massive voids like boots statistically impossible. The probability of forming a void as large and empty as boots through random density fluctuations is less than 1 chance in 10 million. This extraordinary rarity suggests that either our understanding of early universe conditions is incomplete, or that additional physical processes operated during the formation epoch that current models do not include. Computer simulations that start with the observed cosmic microwave background temperature patterns consistently fail to produce voids as extreme as boots. Even when scientists adjust the simulation parameters to the most favorable values possible, they cannot create such massive empty regions through gravitational evolution alone. This failure indicates fundamental gaps in our theoretical understanding. Some cosmologists propose that the early universe contained phase transitions, similar to water freezing into ice. During these transitions, regions with different properties might have formed, creating boundaries where normal structure formation was suppressed. Cosmic voids might mark the locations of these phase boundaries, representing regions where matter exists in a different quantum state. Alternative theories suggest that primordial black holes formed in the early universe might have played a crucial role in creating cosmic voids. If these black holes subsequently evaporated through Hawking radiation, they could have created expanding bubbles of empty space that evolved into the voids we observe today. The energy released during black hole evaporation might have been sufficient to blow away all surrounding matter. Modified gravity theories offer another potential explanation for void formation. If gravity operates differently on cosmic scales than Einstein's general relativity predicts, then structure formation might proceed differently than current models assume. Some modified gravity theories naturally predict the formation of large cosmic voids without requiring extreme initial conditions. The void's properties also challenge assumptions about dark matter's behavior in the early universe. Most cosmological models assume that dark matter interacts only through gravity, but void formation might require dark matter to have additional interactions that allow it to be expelled from certain regions. These dark sector interactions could operate during the early universe while becoming negligible at later times. Measurements of primordial element abundances in void regions provide additional constraints on early universe models. The few galaxies within voids show unusual chemical compositions that suggest they formed under different conditions than galaxies in normal environments. These compositional differences might preserve signatures of alternative nucleosynthesis processes that operated in underdense regions. Advanced statistical analysis of cosmic structure reveals correlations between void properties and cosmic microwave background temperature patterns that extend across much larger scales than current theories predict. These long-range correlations suggest that the physics responsible for creating voids operated on scales approaching the size of the observable universe itself. Some theoretical models propose that cosmic voids represent regions where the Higgs field, responsible for giving particles their mass, settled into a different vacuum state during the early universe. In these regions, particles might have different masses than in normal space, preventing normal structure formation processes from operating efficiently. The void's impact on cosmic evolution extends far beyond its own boundaries, affecting structure formation across regions spanning billions of light years. This suggests that void formation represents a global process that shaped the architecture of the entire observable universe, rather than a localized phenomenon affecting only specific regions. These challenges to early universe models have profound implications for understanding how cosmic structure formation connects to particle physics and quantum field theory. The Boots void might preserve quantum mechanical signatures from the universe's first moments, when the boundary between classical physics and quantum mechanics operated on cosmic scales that dwarf anything achievable in terrestrial laboratories. During the earliest epoch of cosmic history, when the universe was smaller than a subatomic particle, quantum mechanical effects dominated all physical processes. The universe itself existed in a quantum superposition of states, with different possible configurations coexisting simultaneously. As cosmic expansion stretched these quantum states to macroscopic scales, they became frozen into the classical structures we observe today. Cosmic voids like Boots might represent fossilized quantum fluctuations that have been preserved since the universe's quantum epoch. The void's extreme properties, its size, emptiness, and unusual expansion rate, but could be direct manifestations of quantum mechanical processes that operated when the observable universe was smaller than a proton. The mathematical description of quantum vacuum fluctuations predicts that empty space should contain virtual particles that spontaneously appear and disappear on timescales too short to observe directly. During cosmic inflation, these virtual fluctuations were stretched beyond the quantum scale, becoming real particles and energy that contributed to the matter and radiation we observe today. Cosmic voids might represent regions where this process operated differently. Theoretical calculations suggest that quantum entanglement from the early universe might still exist across cosmic distances, connecting distant regions of space through invisible quantum correlations. The Boots void's unusual properties might result from its quantum entanglement with other regions of the universe, creating non-local effects that influence structure formation across vast distances. The void's impact on the cosmic microwave background creates interference patterns that might preserve information about the quantum state of the early universe. These patterns represent a kind of cosmic hologram, encoding quantum information from the universe's birth in the temperature and polarization variations of the ancient radiation. Some quantum field theory models predict that vacuum energy should behave differently in regions of extreme underdensity. The quantum vacuum within cosmic voids might exist in a different state than the vacuum in normal regions of space, creating effective repulsive forces that prevent matter from accumulating. This quantum vacuum effect could explain the void's mysterious expansion properties. Measurements of quantum correlations in the cosmic microwave background reveal patterns that extend across angular scales much larger than the cosmic horizon at the time the radiation was emitted. These superhorizon correlations provide direct evidence that quantum mechanical effects operated on cosmic scales during the early universe, supporting theories that connect cosmic voids to primordial quantum processes. The uncertainty principle of quantum mechanics places fundamental limits on how precisely we can know both the position and momentum of particles. During the early universe, these quantum uncertainties might have created regions where matter density could not be precisely defined, leading to the formation of cosmic voids, where the quantum uncertainty in matter distribution became macroscopically manifest. Advanced theoretical models propose that cosmic voids might be quantum mechanical scars left behind by the collapse of the universe's original quantum wave function. As the universe evolved from a quantum superposition to classical reality, certain regions might have been left in intermediate states that appear as cosmic voids in our classical observations. The void's extreme isolation might provide a natural laboratory for detecting quantum mechanical effects that would be overwhelmed by classical physics in denser regions. Some proposed experiments involve using cosmic voids as quantum resonators to amplify subtle quantum signals that could reveal the universe's quantum mechanical origins. Quantum tunneling effects might have played a crucial role in void formation, allowing matter to spontaneously disappear from certain regions and reappear elsewhere. These quantum tunneling events would be impossible to observe directly, but their cumulative effect over cosmic time could create the extreme emptiness observed in supervoids like Boots. The connection between cosmic voids and quantum mechanics represents one of the most speculative but potentially revolutionary areas of modern cosmology, offering the possibility of directly observing quantum effects on the largest scales in the universe. Next-generation space telescopes and ground-based observatories will revolutionize our understanding of cosmic voids, potentially revealing whether these empty regions contain hidden forms of matter, energy, or even evidence for physics beyond the standard model. The James Webb Space Telescope, with its unprecedented infrared sensitivity, is already beginning to detect extremely faint objects within cosmic voids that were invisible to previous instruments. These observations are revealing populations of ultra-low-mass galaxies and isolated stellar systems that challenge our understanding of how stars and galaxies can form in such underdense environments. Future extremely large telescopes, with mirror diameters exceeding 100 feet, will be capable of detecting individual stars within void galaxies located billions of light-years away. These observations will provide detailed information about stellar populations in isolated environments, revealing how galaxy evolution proceeds differently in cosmic voids compared to normal regions of space. Advanced gravitational wave observatories, including space-based detectors like LISA, will monitor cosmic voids for signals that might indicate the presence of primordial black holes, cosmic strings, or other exotic objects that could be more common in underdense regions. The void's extreme emptiness makes it an ideal laboratory for detecting weak gravitational wave signals that would be masked by background noise in denser regions. Radio telescope arrays spanning entire continents will map the distribution of neutral hydrogen gas within cosmic voids with unprecedented precision. These observations will reveal whether voids contain significant amounts of invisible matter in the form of cold gas clouds that emit no visible light but can be detected through their radio emissions. Next-generation cosmic microwave background missions will measure temperature and polarization fluctuations with sensitivities approaching the fundamental limits imposed by cosmic variance. These measurements will detect subtle signatures of matter within cosmic voids and provide new constraints on the physical processes responsible for creating such extreme emptiness. Neutrino observatories buried deep underground will search for unusual signals originating from cosmic void directions. These detectors might reveal whether voids contain concentrations of exotic matter that interacts primarily through the weak nuclear force, remaining invisible to electromagnetic observations, but detectable through neutrino emissions. Future dark matter detection experiments will use cosmic voids as control regions to search for evidence of dark matter, self-interactions, or decay. The extreme underdensity of voids makes them ideal laboratories for detecting subtle effects that would be overwhelmed by background signals in regions of normal dark matter density. Advanced computer simulations running on exascale supercomputers will model cosmic void formation with unprecedented resolution and physical realism. These simulations will include detailed treatments of dark matter physics, quantum effects, and exotic matter states that current models cannot accommodate due to computational limitations. Space-based X-ray observatories with collecting areas exceeding current missions by factors of hundreds will search for hot gas and energetic processes within cosmic voids. These observations might reveal whether voids contain significant amounts of matter in forms that current surveys cannot detect. Precision astrometry missions will measure the tiny gravitational effects that cosmic voids exert on nearby stars and galaxies. These measurements will provide independent constraints on the total mass content of voids and might reveal whether they contain significant amounts of invisible matter. Future surveys will catalog cosmic voids throughout the observable universe with statistical completeness, creating databases containing millions of void systems with measured properties. These large samples will provide the statistical power necessary to distinguish between different theoretical models of void formation and evolution. Multi-messenger astronomy, combining gravitational waves, neutrinos, cosmic rays, and electromagnetic observations, will provide comprehensive views of cosmic void properties that no single type of observation can achieve independently. These coordinated campaigns will reveal whether voids are truly empty or contain exotic forms of matter and energy. Quantum sensing technologies might eventually become sensitive enough to detect quantum mechanical effects preserved within cosmic voids since the early universe. These experiments could provide direct observational tests of quantum gravity theories and the quantum mechanical origins of cosmic structure. The combination of these observational advances promises to transform cosmic voids from mysterious empty regions into detailed laboratories for studying fundamental physics under extreme conditions that cannot be replicated on Earth. Our journey through the Boots void has taken us to the edge of cosmic understanding, where the universe reveals its most profound secrets through the language of emptiness itself. We have seen how this 300 million light-year hole in space challenges everything we thought we knew about cosmic structure, dark matter, and the forces that shape reality on the largest scales. From its impossible emptiness to its 8 lonely survivor galaxies, from its gravitational mysteries to its quantum echoes from the universe's birth, the void represents one of the most significant discoveries in modern cosmology. The Great Nothing forces us to confront uncomfortable truths about our cosmic destiny. As dark energy continues its relentless expansion of space, the entire universe will eventually resemble this void, empty, cold, and profoundly alone. Yet this knowledge makes our current cosmic golden age all the more precious, reminding us that consciousness and complexity exist as remarkable victories over entropy and isolation. Perhaps most importantly, the Boots void teaches us that even nothingness can be profound. In studying cosmic emptiness, we discover new physics, ancient history, and fundamental truths about the nature of existence itself. The void stands as proof that the universe contains mysteries that exceed our imagination and challenges that will drive scientific discovery for generations to come. As we continue to probe deeper into cosmic voids with ever more sophisticated instruments, we move closer to answering some of the most fundamental questions about reality. What is dark energy? How did cosmic structure form? What is the ultimate fate of consciousness in an expanding universe? The Boots void awaits our future explorations, holding within its emptiness the keys to understanding forces and phenomena that operate on scales from quantum mechanics to cosmic evolution. In the Great Nothing, we find not absence, but the presence of the universe's most profound mysteries. If you found this journey into cosmic emptiness as fascinating as we did, subscribe for more explorations of the universe's most extraordinary phenomena. The cosmos holds secrets beyond imagination, and each discovery reveals new questions that drive us deeper into the mystery of existence itself. The void calls to us across 300 million light-years of emptiness, reminding us that even in nothingness there is everything left to discover.